Hello everybody, I hope you can hear my voice well today. Uh, in this video, I'm going to actually talk to you about the rate equations for three-level laser system. So let me tell you that a three-level system will only have three energy levels, and the system could be an atom or a molecule, an ion, yeah, something like that. And you can label the energies and number density. Let me tell you that if you have one three-level system, which could be an atom, a molecule, or and as I said, it could be having energy levels as number 1, number 2, and number 3. And energies of these levels, you can actually label them as E1 energy, E2 energy, and E3 energy. And in case if the electron sits in level number 1 in one three-level system, then this is actually called some kind of category of three-level systems where electron is sitting in the lower level. And if you count such three-level systems, and if you get the number to be some value, and if you divide that by the volume of the collection of these three-level systems, then you get something called number density of three-level systems with the electron in the lowest energy level. Okay, so this is actually the definition of N1. N1 is number density of three-level systems where you have got the electron in them in the lowest level. And in some three-level systems of the sample that you're considering, electron will not be in E1 level, and it will not even be in E3 level, but it will be in E2 level. And if you count such kind of three-level systems, and if you divide that number, the counted number, by the volume of the sample of three-level systems, then you get something called the number density of two-level systems with the electron sitting in the level number 2. That's the definition of N2 actually. And similarly, N3 also you can define as the number density of three-level systems where you have got electron sitting in the topmost energy level, which is E3 level. So this is actually N3 is actually number density of the three-level systems where you have got electron sitting in the topmost level. And the sample that we're considering, the sample that we're considering could be having some number of atoms, number of three-level systems actually. And if you divide that number of three-level systems divided by the total volume of that sample that we're considering, you will get number density of in general three-level systems. So this N, which I'm calling, is actually general number density of three-level systems, which could be involving N1, and it could be also involving N2 kind of three-level systems, and it could be involving N3 kind of three-level system. That means our sample that we're considering for the three-level systems is involving three-level systems with electron in the lowest possible level, and three-level systems with electron sitting in the second level, and it's also involving three-level systems with electron sitting in the topmost level also. So let us call this as our equation number 1. So by Boltzmann's distribution, what happens is usually we have this inequality for the number densities N1, N2, and N3. that's actually n1 is always greater than n2, and that is always greater than n3. And the scheme for the three-level system is that when we have this number density of this lower level bigger than the number density of n2, and that's bigger than n3, then what we do is we actually pump this let us consider only one we pump this sample of three-level systems such that the pumping photon will actually take the population from this level number 1 to level number 3 actually. So it will excite the three-level system, electron in the lowest level to go to the topmost level, and from there what happens is, of course this is actually done by pump, that's why I will call this thing with the help of W sub P for pumping, and this W sub P I'm writing with intention, which you will see when I write the rate equation. But anyways, it is actually kind of making the transition, electronic transition from level number 1 to level number 3, and from there the electron which is sitting in the level number 3 will relax very quickly by non-ready to decay process to level number 2, and level number 2 is actually kind of long-lived state. That means it's actually a metastable state. So between level number 2 and level number 3 we'll be having laser action taking place. That means between number 2 and number 1 level we'll be having stimulated emission process dominating, giving rise to laser output actually with a frequency which is actually E2 minus E1 divided by H. So anyways, so if you want to have the lasing action between level number 2 and level number 1, we will have to actually invert this condition. Wait a second, the first two things actually. This condition will have to invert. That means we will have to make the population of N2 being more than population of N1 if you want to achieve amplification of the photon flux, as explained in a couple of videos back under the video title laser principle. So to achieve amplification of photons or maybe laser action, we should actually need N2 being greater than N1, and that's what we call as population inversion. So within a few after a few mathematical calculations in this video itself, what we do is we'll see where we can get how we can get this delta n is equals to n2 minus n1 as more than 0 positive quantity. How can we get it, and what is the necessary condition and threshold kind of pumping power that we require for achieving this population inversion. So anyways, let me start writing rate equations for n3, n2 and n1 also. So okay, so this is the thing. So I need space for writing those rate equations, so let me actually erase these things only. But remember, I am calling this as equation number 1, which is for the total number in state n. So for the case of n3, I can write the rate of change of n3 dn3 by dt as remember we are pumping these n1 states, n1 population, to actually convert into n3 population because of absorption process. And the rate equation, the equation which we consider for absorption process involved something like W1, 3, and then number density of the lower levels. This was the kind of equation which we wrote when I explained some topic called cross sections, rate equations in terms of cross sections. Over there we actually for absorption process we wrote 1 3 because it is starting from level number 1 and it is taken to level number 3 1 3. And I also told you that this 1 3 W13 is actually written in terms of cross sections as sigma 1 3 and F, which is the flux of incident photons. So in this case we are actually causing the absorption of pump photons. That's why this I will write this W13 as simply WP actually, which is for the pump, W sub P, pump. So for that reason I will write the first term, which is because of absorption, as W sub P into N1. And because of absorption process, the number of N3s will increase actually. These N1s will convert into N3s. That's why this term is coming with plus sign. But once when the electron reaches here, the pump photon can also stimulate this electron to go backwards onto level number 1. So the reverse process also can happen. That means electron can now it can now come from level number 3 to level number 1. So with again same kind of coefficients. That means this time we should be writing sigma 3 W31 into N3 actually for stimulated emission process between level number 3 and level number 1. But as I said, this W31 which can be written in terms of the cross sections like this. Again I'm writing as WP because this W31 is also equal to W13 if we don't have any degeneracies for these levels. That's why we can write this WP actually over here for even W31. So the second term also can be expressed in terms of WP like this. But remember, this is coming because of absorption, and this term is coming because of stimulated emission between level number 3 and level number 1. And we can also have some radiative and non-radiative decay processes. That means radiative means which could be because of spontaneous emission, and the other thing is non-radiative decay process. So we can also include this 1 by some time 3 2, and of course this process will be actually proportional to N3. So this means here we are having two processes, radiative decay process and non-radiative decay process. Radiative is because of spontaneous emission, that is from level number 3 to level number 2, and non-radiative is again from here to here, which I'm including in this term here. Of course you should be remembering that 1 by T32 is also equals to 1 by T32 because of spontaneous emission, that is I'm writing as R for radiation, and because of non-radiative decay process, which I'm writing as N here. Of course this equation I wrote in the last video, which was on pumping schemes, second part video. So over there you will be able to see this thing. So this term is actually because of spontaneous emission from level number 3 to level number 2, and also because of non-radiative decay from level number 3 to level number 2. And of course a similar kind of process can also happen between level number 3 and level number 1. So the last term could also be included with same kind of nature as this one. So again, because of this process also the population of N3 decreases. Sorry for this disturbance, I'm getting phone connections. I'm extremely sorry, I should have put my phone on aeroplane mode, but anyways, that was a small disturbance I think. So yeah, so again this can be included here with a negative sign because of this process also the population of N3, level number 3 will decrease. That's why this is coming with a negative sign. And as I said, even this can also be because of both radiative and non-radiative processes. That means 3-1 radiative, which is actually spontaneous emission between level number 1 and level number 3, and non-radiative 3-1 and N. So we can write it like this. So anyways, what we do is we actually assume that this 1 by t31 is actually kind of much large number. I mean, wait a second. t31 itself is a very large number. So the probability, so from here to here, we may not have much transition. It's gonna live here for a long time if we actually want to come this one to this one spontaneously. So if we consider it like this, then we can neglect the last term actually. We can neglect the last term, and after neglecting the last term, we can actually write the remaining equation as dn3 by dt is equals to wp into n1 minus wp. Of course, in these two terms we can actually take n3 as a common factor out, so this is wp plus 1 by t32, and outside of this we can write n3. This one I can call as equation number 2, right? Equation number 1 was for n, total n, which is n1 plus n2 plus n3, and this one is for dn3 by dt. Right, so what I do is now I can also write some equation for dn3 by dt, which is a right equation for n2 actually. So let me start writing that equation. So dn2 by dt, as I am saying that I'll be having laser action between level number 2 and level number 1. This N2 population could be gaining because of absorption of lasing photons from level number 1. So we can write similar kind of term that we wrote for N3, dn3 by dt, with absorption of pump photons, but now here it will be absorption of lasing photons. That's why I will write this W sub L, and of course this is gaining from level number 1, that's why N1. And again I can have loss of lasing photons because of stimulated emission between level number 2 and level number 1, so I should be writing W sub L, and again this time it is N2 because it is between 2 and 1. And I am gaining this population from level number 3 by the process 3 to 2. That means it is actually because of both non-radiative decay and also radiative spontaneous emission between 3 and 2. Since I'm gaining, I'm putting a plus sign here, and it is proportional to N3 population, that's why N3 here. And I can again have loss of this population to level number 1, so I can write something like T from 2 to 1, and of course it's proportional to the population density, population of level 2, that's why it is N2. And again I can have this T21 involving both radiative spontaneous emission, or it could also be involving non-radiative decay from level number 2 to level number 1. So this term it is including both radiative and non-radiative transitions from level number 2 to level number 1. So this is the equation for our dn2 by dt. So I can call even this as equation number 3, and of course from equation number 1, which was for total population of the sample of 3-load system that we're considering, we can write, since this n is actually a constant, n is n1 plus n2 plus n3 and n3, so as it's a constant, so we can say that dn by dt is 0. It won't change. The number of these systems is not changing. The total number is not changing. So if you take this condition, then we can say that dn1 by dt is simply negative of dn2 by dt minus dn3 by dt, because if you take all of them together combined, you should be getting 0 as the answer from this condition. So anyway, so that's why we cannot write dn1 by dt for now, because it is simply summation of dn2 by dt and dn3 by dt with a negative sign in front. So yeah, we have got the important two equations, which are actually equation number 2 and equation number 3 for our discussions. But yeah, I may have to erase the space over here, I think, but yeah, we can do that thing, I think. So let me erase the space, I mean some of the thing on the board here, and let me tell you the way we go towards finding n2 minus n1 value is we start with something called steady state. So at a steady state, I'll put this symbol at the rate for it, but anyways, I should have put 80 also. But at steady state, what happens is dn3 by dt is equals to 0. So it is equal to 0. So n3 won't change as a function of time at steady state. So from equation number 2, if you put this entire thing, I mean right hand side of this one to 0, then we can actually write n3 in terms of n1. So n3 into this entire thing. So within this also we can take this t32 as common factor out. So t32 into wp plus 1 whole divided by t32. This entire thing should be equals to wp into n1. So this entire thing, if you put equals to 0, and if you take common factor t32, I mean least common factor LCM, then you will get this one. And if you write this for n3, this will go I mean by cross multiplying this one, making it wp into 3, I mean t32 divided by t32 into wp plus 1, and outside of this n1, and I can call this as equation number 4, which I will write when I actually kind of simplify the equation for this one by using the condition again. Steady state, at steady state, even dn2 by dt is also 0. So anyways, to write those steps, I will have to erase these equations. So from equation number 3, we can put the right hand side of it being equal to 0, and within that I can also substitute for the value of n3, which is from equation number 4, this entire thing. So let me do it in step by step, I think. So first thing is I'm writing wl into n1, this term as it is, and this term and the last term I will write together. So that is actually minus in bracket I can put wl plus 1 by t21, and outside I can write n2 as it is common to both the terms, and plus 1 by t32, and instead of n3 I will write this entire thing from equation number 4. So this is actually t32 wp divided by t32 wp plus 1, and outside of that it is n1. I can cancel out t32 here and here. Okay, and I need space, so let me start erasing all this thing. And within the, of course, this entire thing was equals to 0. That's what is the meaning of dn2 by dt being equals to 0. So this term and this term, if I can cancel out this and this, and within these things I can take n1 as common factor out. So if I take n1 as common factor out, I'll get wl plus wp divided by t32 into wp plus 1. I may have to put this bracket like this now, and since it is having negative sign here, so if I send it towards the other side of the equation, then it will become wl plus 1 by t21 entire thing being multiplied to n2. So I can even do some simplification over here, I think. So n1 into WL and T32 WP plus 1 plus WP all divided by T32 WP plus 1. This entire thing is equals to simply WL. Of course, over here also I can do some kind of LCM calculation, I think. So this will be WL into T21 plus 1 divided by T21. This entire thing is multiplying to n2. So from this equation also what I can do is I can actually write something for n2. So n2, if I write, it will be this T21 will go and multiply this each of these terms, so it will be WL into T21. Of course, within the bracket I still have this T32 WP plus 1, and in the next term where it multiplies, you can write WP into T21, and you can close this bracket like this, and in the denominator I can write T32 WP plus 1 into T21 WL plus 1 into N1. So this is actually for the value of N2 in terms of N1. And remember what I told you is that to achieve the population inversion between N2 and N1, we need to actually focus on calculation of N2 minus N1 and see where it can become positive. So this is actually for N2 value, and this is the only equation which I really concerned right now. I'm going to raise the rest of the thing on the board. So from this N2 value, if I define something like delta N as the difference of N2 and N1, I can actually try to calculate that quantity from this equation. So for N2 I can write this entire thing as it is. So this is WL. Of course I can even do some kind of multiplication of these terms. So this will be WL into WP into T21 into T32 plus over here it is WL into T21, right? And in the last equation we can write as it is WP into T21, last term we can write as this, and in the denominator we can write T32 WP plus 1 into T21 WL plus 1. So this entire thing into N1 is actually for the value of N2, and of course minus N1 we can write as it is minus N1. In the next step we can write this entire thing as it is, and we can take N1 as common factor out. So if you take N1 as common factor out, which you can write in front now, within the bracket we can actually see that this entire thing minus 1 actually. So if you take LCM this entire thing, so this entire thing will come as it is. I mean this all numerator will come as it is, and within the denominator we will be having these two things, this and this, and minus you will be having T32 WP plus 1 into T21 WL plus 1. So again we'll have to actually compute product of two I mean these two terms actually, this and this. So we can write this N1 this entire thing is nothing but this numerator here. So let me write it this time because we'll need this now. So WL WP T21 T32 plus WL. Maybe I can take this thing as common factor or WP, but it will get cancelled out in some time. So let me even write this one as it is. So WL into T21 plus WP into T21, of course, yeah. And now product of these two terms. So this is a WP WL T21 T32 and minus T32 WP minus T21 WL and minus 1. Entire thing divided by T32 WP plus 1 to T21 WL plus 1, and of course we can close this bracket like this. So this is actually for delta n, which is n2 minus n1. We substitute for n2 value here and n1 value, n1 as it is here, and in the next step I will take the n1 as common factor out, so this entire thing will come here with like this. I mean this numerator and this denominator with these two brackets like this, minus 1, and this numerator will come here as it is, and this denominator with these things will come here, but this time we have done LCM, so this multiplies here with a minus sign. And if you expand, if you write these things as it is, and if you expand these two terms, it will give you this one. But now we can observe quickly that this term is equals to this term with a negative sign, so these two things will get cancelled, and T32 term, I mean WP into T32, it won't get cancelled, but T21 term with WL, this one will get cancelled. So what we get is finally N1 into, if you observe this term is WP, and this is T21 minus, here it is actually same thing but with 32 minus 1, and the whole thing divided by T32 WP plus 1 into T21 WL plus 1. So this is actually for our delta n. This is expression for delta n actually, involving WP and T1 to T32. And of course when n1 is not equals to 0, to have this delta n as a positive number, what we need is the denominator also as a positive number. So to have this delta n as positive, then we need this WP into T21 minus T32 minus 1, it should be more than 0. And of course this WP will always be a positive number, and to have this entire thing more than 1, actually if you send this thing toward the side, it will become, this thing should be more than 1. So to have that condition, we need necessarily this T21 minus T32 as more than 0. We need this condition, we need this one to have this quantity as positive quantity, otherwise it will become negative here. So this is actually necessary condition for the 3-level system to have population inversion between level number 2 and level number 1. And at threshold, what we expect is we expect this delta n to be 0. So at threshold value for just before lasing, I mean just before population inversion, we expect this delta n to be 0. So that threshold power which we can write as W sub P and T for threshold will be simply T21 minus T32 minus 1 will be equal to 0. So instead of being greater than 0, we equate it to 0. So at threshold, this is the thing. So from this, if we invert for W sub PT, then we get the threshold pumping power in terms of the time constants. So at threshold, the pumping threshold is simply 1 divided by T21 minus T32. This is it. So this is actually so if the pumping power is more than this one, then we start having delta n being greater than 0, and because of this population inversion, we start having stimulated amplification. Amplification of the lasing photons by stimulated emission of radiation, giving rise to the laser action between level number 2 and level number 1. So this is actually the topic on rate equations for 3-level system. I hope I made some useful lecture here, and you can actually comment on the notes which I explained here, and I will meet you next time with some other video. Thanks for watching. Bye bye for now.